My name is Thomas Brazelton. I'm a PhD student at the University of Pennsylvania. I'm co-advised by Mona Merling here at Penn and by Kirsten Wickelgren at Duke. I'm interested in homotopy theory, especially motivic and equivariant homotopy theory, as well as enumerative geometry and the interplay between these two fields. I'm currently applying for postdocs, hoping to start postdocs next fall. Enumerative geometry is a classical field of math which asks geometric questions of the form how many and expects integral answers. Apollonius asked in 200 BC, if we have 3 circles on the plane, how many other circles could we draw which are tangent to all 3? Bézout in the late 18th century studied the intersection of planar curves of degrees m and n. And in the 19th century, Salmon and Cayley asked about lines lying on a cubic surface. This is an example that we'll revisit in a little bit. And over the complex numbers, all of these questions in well-defined solutions. There are 8 circles tangent to any 3. There are m times n points of multiplicity, counted with multiplicity. This is Bézout's theorem. And there are 27 lines on a smooth cubic surface. So if we zoom into this Apollonius problem, we note that if I deform the black circles, then these 8 solution circles are going to grow and shrink and translate in order to accommodate tangency to the black circles as they change. But in particular, no new solutions will be created and no existing solutions will be destroyed. This is something that Schubert called the principle of conservation of number, and it's really what makes enumerative geometry so interesting. Another way of thinking about this is that under small parameterized continuous changes in the black circles, this number 8 is invariant. In other words, it's invariant under certain homotopies that really structurally preserve the property that these black circles are in fact circles. So there's 2 components to enumerative problems like this. There's a global solution and there are local contributions. In the case of Bézout's theorem, a global solution is just the total number of points that we're counting. The local contribution is the intersection multiplicity at a given point of intersection. And this global solution is a sum over all the points of intersection of their local contributions to the global solution. Often we can rephrase enumerative problems in terms of a section of a vector bundle. A given conic on the plane, pictured in red, defines a section of the bundle O of 2 over CP2, while a cubic in blue gives you a section of O of 3. The global solution is the Euler number, or the top Chern class of this bundle, in this case 6, there's some points of intersection of multiplicity. And the local contribution is the Brouwer degree of the intrinsic derivative of the section at a point. This is often complicated to compute, but there's 2 interesting facts. The first is that the Euler number is Poincare dual to the 0 locus of a generic section. This is a classical result in topology. And this tells you if you want to compute an Euler class, what you have to do is pick a generic section and count the local contributions of it. In other words, this tells us that the global solution is a sum of local contributions. The second fact that we see is that the Euler number is independent of the choice of section. It's an invariant on the bundle, not on a given choice of section. In particular, the sum of local contributions over any section is going to be the same. And this is what we call conservation of number. If I picked a different conic and a different cubic, this gives me a different section of O of 2 plus O of 3, but the sum over intersection multiplicity at each of their points is still going to be the same. Abstract enumerative geometry can be thought of as any time where we're asking these geometric questions, but we're looking for answers that are richer than integers. One direction is a program of math called A1 enumerative geometry, in which we use tools from A1 homotopy theory to study enumerative geometry over arbitrary fields. We get enumerative answers that are valued in Grothendieck of your field, which we can roughly think about as symmetric matrices over K. And our classical answers are recovered by taking the rank of this matrix. And we get more and more interesting data as the field becomes a little bit more complicated. Over the reals, intersection multiplicity in Bézout's theorem picks up a sign. In other words, when 2 curves cross, we can orient them, and we can see if they had a right-hand crossing or a left-hand crossing. This follows from more general work of Stephen McKean. Over finite fields, the invariants that you need to classify a symmetric bilinear form constrain the fields of definition of solutions. And a really great example of this is in Cass and Wickelgren's paper about computing 27 lines on a smooth cubic surface over an arbitrary field. Local contributions would require you to know about the Brauer degree in the A1 setting, and the definition of this Brauer degree is due to Morel. Cass and Wickelgren proved that local Brauer degrees at rational points are EKL forms, and these are computational commutative algebra formulas that were developed in the 1970s by Eisenbud, Kimchiashvili, and Levine, and were conjectured to be more general. Together with some authors, we proved that along a finite separable extension, local degrees can be computed by base changing upstairs and transferring data down along the field trace. Together with Stephen McKean, we proved that in the univariate case, you can still lift and transfer data even when the residue field is not separable. In particular, we gave a complete structural classification of Brauer degrees in the univariate setting. Finally, with Stephen McKean and Sabrina Pauli, we proved that local Brauer degrees can be computed independent of assumption on the residue field, so not even separable. In particular, we can compute them using code that we wrote for SAGE. This is a very efficient code for computing these types of degrees. In particular, this result makes enumerative geometry accessible over imperfect base fields, which is not something that we had before. So if we go back to the classical setting, we can ask what happens if we introduce some equivariance into the picture. Recall that a cubic surface is the vanishing locus of a degree 3 homogeneous polynomial sitting inside of CP3. Salmon and Cayley proved that there are 27 lines on any smooth complex cubic surface, but this doesn't hold over the reals. Schläfli later proved that on a smooth real cubic surface, we see either 3, 7, 15, or 27 lines. We would say that a cubic surface is S4 symmetric, or I would say symmetric, if either of the equivalent conditions hold. Either F is a symmetric polynomial in x0 through x3, or under the S4 action on CP3 by permuting coordinates, we have that x is just mapped back to itself. But this action is linear, so it sends lines to lines in CP3. In other words, if x is symmetric, lines on x are sent to other lines on x. So our 27 lines now come in S4 orbits, and we can ask, what are these? And we can also ask, do they depend on anything about x other than the fact that it was symmetric? More generally, we can ask for a notion of equivariant conservation of number. In other words, if possible solutions to an enumerative problem come with a G action, are the G orbits of the solutions conserved? And the answer is yes. And I have a lot of fine print up here, but I'll just say the punchline, which is that we have a well-defined Euler number associated to an equivariant complex bundle valued in the representation ring of G. On the left, this Euler number is a complex G representation. The classical answer is recovered just by taking the rank of this representation. On the right, local contributions are isotropy and multiplicity. And the quick way to say this theorem is that the sum of regular representations of the orbits of solutions is conserved. And we can leverage this result to begin to answer these types of questions about enumerative geometry when there is a group action. So we can prove that the 27 lines on a smooth complex cubic surface, smooth symmetric complex cubic surface, always have the same S4 orbits. We see 12 lines with isotropy group C2. We see another 12 lines with isotropy group C2 prime, and this is denoting the 2 non-conjugate copies of C2 sitting in S4. And finally, we have 3 lines with isotropy group D8. And here, all of these lines are pictured on the Clebsch cubic surface, grouped together in orbits by color. Recall the Schläfli theorem that says that on a smooth real cubic surface, there are 3, 7, 15, or 27 lines. Under the presence of symmetry coming from this group action, we can actually refine these classical results. We can say that on a smooth symmetric real cubic surface, we only see 3 or 27 lines. The Clebsch here is a good example of the 27 lines, and the Fermat, for example, is an example of the 3. So thank you very much. I've attached my website here, and I'm happy to talk about any of this or anything else in the breakout rooms. Thank you.